faster because it's got less inertia, right? The medium has less inertia. So this is like oxygen, low frequency, right? This is like helium. Yeah? You fill your mouth. Now I'll use the flawed connectors. Oh, let me just show you this guy. This is kind of fun. Ooh, that's faster, right? Ooh. Okay. Move your head. You know, if somebody says move your head, just go, okay. Can you move? Yes. I don't know why that matters. Okay. I think I know what the answer is. The answer is... Just call me Murray. Did I give her a heart attack?
A little bit.
This is how you break them, by the way. Oh, there you go. Look at that. It's just like downtown.
I like that.
Okay, now watch, if you would. I'm going to send a pulse down this way. Here we have a medium where the speed of the waves is slow. Here's a medium where the speed of the waves is fast. And this is a bit like water. This is a bit like water. This is light traveling through water. It slows down. It's about 30% slower in water. And then when it gets to air, it speeds up. Okay? So first thing I want to do is, let's just see what happens to the wavelength. What's happening to the wavelength as it goes out into the air?
Lengthening.
It's like,
Yeah, it's a bigger wavelength, isn't it?
yeah.
Does this make sense? Remember the formula is V is F lambda, right? So therefore lambda is V over F. F is the same. Watch when I do this. The F for this whole medium, the F is the same. You convince yourself that they're all going up and down at the same rate, aren't they? Okay? So the frequency is the same. It's just that the velocity is bigger, so if the velocity is bigger, the wavelength is bigger. Here the velocity is bigger, you've got a bigger wavelength. Here the velocity is slower, so you have a slower wavelength. Okay? Which?
The yellow one.
I don't know. Are there two that are? Isn't that funny? Oh, those are the ones I fixed, so I put them on backwards. That's kind of funny. That is kind of funny. All right, now, I wasn't going to show you that, but put that in the back of your mind because we're going to talk about, this is called refraction, and this is one dimension. Okay? But I just want to show you this. I'm going to send an up pulse. Now, relative to this medium, is this medium fixed or is it free? It's freer, right? It's not totally free, but it's freer. It's easier to move than this. So if I send an up pulse, first there should be a reflection off this boundary because that's an abrupt change. So watch. I'm going to send an up pulse. Watch, there'll be a reflection. You see it? See a little reflection? And do you see that the reflection that comes back is upright? Do you see that? Watch again. Up pulse. You're going to see a reflection right off there. Here it is. See it? That one's upright. Do you see that? Okay? And then there's also, by the way, a transmitted pulse. So some of the light gets out of the water into the air, and it goes this way, and then of course it reflects off the no air boundary there, right? Okay. Now, if I send a pulse this way, there's an abrupt change. There should be a reflection that comes back. Is this, relative to this medium, is this fixed or free? It's more fixed. It's got more inertia, right? So it's more like a fixed surface. So I'm going to send an up pulse. You got to look quickly because it moves fast. I'll send an up pulse. Look what comes back. A down pulse came back, didn't it? There we go. Here we go. Let's try it again. I'll send a up pulse again. Down pulse comes back. You see that? Okay, so it's not, it doesn't have to be totally fixed or totally free. It just has to be relatively fixed or relatively free. Okay. Okay. These are